All right, so the title of our notes, we're in section 8.3. And I'm going to define for you logarithms. And a logarithm is another form for an exponent. So we're going to talk about two forms, exponential form, which we're familiar with, and compare that with logarithmic form. So if we have b to the power of x is equal to a, we call b our base, and that's what our last homework was, to get a common base. And then we worked with, we had x as our exponent or our power, and a is our answer, but I'm going to call it the argument. Okay. So we have the three parts here. Base to the power is equal to an argument. Logarithmic form takes those three pieces and puts them in different spots. And you write log, for log, short for logarithmic or logarithm. You take your base in your exponent, and you're going to have a subscript. So that's b right there, but it's going to be as a subscript. You're going to put your argument. Argument's what you're taking. So you got log base b of a is equal to the power. And I know this is foreign to you right now, but this is what log form looks like. And the difference is, so in exponential form, if you know the base and you know the power, you can solve for the argument. Log form is better for solving for a power that you don't know. So like if I know the base and I know the argument, but I don't know the power, that's where this is going to be helpful. Okay? And if you have a scientific calculator, you'll see it's got a button on there that says LOG, and that's what it's going to be used for. It's used for solving for exponents. So again, here's our base for our log. This is our argument. And it's always equal to a power. Okay. There's a couple things that you do want to know. So for our base is always going to be positive. The reason for that is first of all, if you have 0 to any power is going to be 0, so that's not really interesting to us. If the base is negative, what happens as you raise the power? Like -2 squared, -2 to the third, -2 to the fourth. It's going to alternate between positive and negative, and things get a little complicated. So that's why we want to keep our base positive. And also, it's not very interesting if our base is 1. So, because if our base is 1, 1 to any power is going to be 1. So we're gonna say our base has to be a positive number. It can't be 1. Some of you are saying, well, why don't you just say 2 and above? Well, it could be a fraction. It could be 1/2. It could be 0.3. It could be irrational. So as long as it's positive and not equal to 1. Also, if we have a positive base, what can we say about the argument? It has to be positive. Can't be 0, can't be negative. There's no way. So the argument, so we'll say A has to always be positive. The power can be anything. So we know that 2 to the third power is 8. That's exponential form. So if I change that to logarithmic form, it would look like this. Log base 2 of 8 is equal to 3. Means the same thing. One we're familiar with, one we're not. Okay, and so we're just kind of getting to know what the new log form. Or if I have 5 squared is 25, what do I write? Log base 5 of 25 is equal to 2. Okay. So now let's look at number 1 on our homework. We're going to be going back and forth here, but number 1, we have log base b of b squared, and we want to figure out what that's equal to. And so I'm going to set this equal to x, okay, and we know, okay, our b is our base, b squared is the argument, and x is the power. So what you're going to want to do is change it out of this form back into exponential form. Okay, so you notice where the three things are. If I change this into exponential form, my base is b to the power of x, and I'm going to set it equal to what? The argument, which is b squared. So what's x? And then you're done. And often, when you change it out of log form, it's that easy. It just looks hard at first, and then when you get it out of the form, it's something you can do pretty quickly. Next one I'm going to do with you is 9. Okay. So 9 is in log form. What's the base? 9. And the argument is 27. And we want to find the exponent. So I'm going to set this equal to some variable x. You can make it another variable, but I'm going to make it x. And so we're going to change it out of log form and put it into exponential form. And so how would I write exponential form? Nine to the power of x is equal to 27. Okay. And if it's not obvious, you do what we did last section. You try to get a common base between the left side and the right side. What would that common base be? 3. So you change 9 to 3 squared. Change 27 to 3 cubed. And you get 3 to the 2x is 3 to the third. And we can set, because our bases are the same, we can set our exponents equal to each other. 2x equals 3, and x is 3/2. Okay, so really the only new thing that we're doing right now is getting it out of log form into exponential. Once we get it into exponential, it's kind of like the problems we've been doing. So the next one I want to look at is 13, but 13 looks different, doesn't it? You don't see log, you see ln. That's not a I. It's an L, lowercase l. So ln of e to the power 7. And notice there's no subscript, so there's no base either. Okay? So we're going to go back to our notes a little bit, and I need to give you a little background before we hit 13. So there's something called an Euler number. Named after the mathematician Leonhard Euler. And it's the number that he came up with. And we call it E. And it has its own button on a scientific calculator, just like pi does. It turns out to be an irrational number. It's not a number that you have seen much yet, though. But it's something that shows up in finances. It shows up in statistics. It shows up in calculus. So more the higher math. And this is kind of logs is pretty much probably the first time you see this. You guys remember talking about limits a little bit? Limit as something goes to infinity. Here's the definition of E. E is the limit as n goes to infinity of 1 plus 1 over n to the power of n. Okay? You don't have to memorize that or anything. I'm just giving you some context. That approaches this number E. What you want to know is E comes out to be about 2.7. 2.7 is fine. If I give you more decimals, it'd be 1828, but it keeps on going. It's irrational. So it's like the number pi, 3.14-ish, 2.7 or 2.72 if you want another decimal. Okay. So we call this the Euler number. It's also sometimes called the natural number. And it turns out with finances, it's nice to solve using a log base E. The log base E of some number, 5. And log base E gets used so much that it gets its own notation. Instead of having to write log base E each time, they write ln 5. It means the same thing. It's kind of shorthand. ln, n for natural, l for log. They goes backwards. It's log natural or something like that, right? But ln of 5 means log base E of 5. Okay. Let's go back to that problem. Number 13. So we got the natural log of e to the power 7. What you want to know is that this is the same thing as log base what? Base e. And our argument here is e to the 7th, so e to the 7th. So our base is e, our argument is e to the 7th, and we're trying to find out what the power is. See if you can figure it out. Do we have an answer? 7. Because when you change it into the other form, you get e to the x. The base to the power is equal to our argument, e to the 7th. And so the bases are the same, so x is 7. That's it. So not a tough problem. It's just understanding the notation. Next one we're looking at is 18. On 18, what's the base? It's missing. Okay, so we have the argument, which is 1 over 10. We know this is going to be our power, but the base, not sure. And I'm going to explain this as well. What base is our number system in? Okay. So our numbers, so you mean it may have been a little while, but in elementary school, you'd always do the base 10 expansion. So like if you had 325, you'd have to write that as 3 times 10 squared plus 2 times 10 to the first. You never did that? You have your ones place, you have your tens place, you have your hundreds place. Yes. Well, I'm doing it this way for you because you can see that the base is 10. When you in computer science, computers work better with a different base. But you know why we use base 10? We got 10 fingers. That's where it came from. Yes. It's natural. It's a common thing. Okay. In computer science, it's easier to work with only two things, on or off, and so they work in base 2, or they call it binary. When you talk about colors and RGB, um, red, green, blue, the mixtures of those, that comes in base 16, which they call the hexadecimal system. So there's different bases out there. There's different number systems out there, but we work in base 10, and that's because 10 is something that's really common to us. Okay. And so if we write log without a base, by default, that base is going to be 10. Okay, so log base 10 of 5 can also be written as just log 5. So if we write out log without any base, by default it's 10. So there's only two defaults, 10 or E. And so we can't put log for both of them. Log is reserved for 10, ln is reserved for E. And those are the two buttons you'll find on a scientific calculator. You'll see an ln button and an log button. Okay. So back to this problem. So now we know our base is 10. That's the default. Okay, or the common base. So if we change this out of log form into exponential form, it's going to be 10 to the power of x is equal to 1 over 10. Okay. And then it's like a problem that you did yesterday. 10 to the x is 10 to the negative 1, so x is negative. Try number 23. Using the same method, solve for x. Change it out of log form into exponential form. Who's got the exponential form for 23? Not the answer, just the exponential form. Yeah, would e to the third equals x. Perfect. And that's the answer. So ln, remember, is log base e of x equals 3. And when we change it, we go our base to our power. So e to the third equals x. And I'm just trying to solve for x, and I just did. Done. If I have a calculator, I can approximate e to the third, but e to the third is good enough. On 26, 26 is a little different here. We're not going to want to change it out of log form into exponential form because there's a log on both sides of the equation. Any idea what we're going to do on 26? Well, what would our next line be? X squared equals 125. And it's not dividing, but the idea is if I have one log on each side of the equation with the same base, then the arguments must be the same. Right? And so I have a log base 3 here, and I have a log base 3 here. And so my x squared must match my 125. And so I can just, in a sense, drop the log. What's that? And when I take this, what's the square root of 125? You're right. About what? It's not 15. 125 is 5 to the third power. We're looking for a pair. And so this is going to end up being x is 5 square root of 5. Square root of what is 15? 15 would be 225. So it is plus or minus, but no, we're good. It has to be plus or minus. The reason it's good is the argument has to be greater than 0. And if I plug a negative in there, I'm still squaring it. So I can accept x could be negative. It's the argument that can't be negative. So I do want the plus or minus. Okay? All right. Want to do one last? Well, what is 31 in exponential form? Atticus, help me out with this one. What is 31 in exponential form? What's the base? What's the power? And what's the argument? 1. Okay. So what could x be? Could be anything that it's allowed to be. What did I say about the base? What's the base allowed to be? Anything that's positive, but not 1. Okay, so x is all real numbers such that x is positive and x is not equal to 1. So anything else. Decimals, yeah. Yep, that would work. Huh? All positive real numbers except for 1. That would work. All right, so we're going to do a little, we did some graphing already in the first homework, but we're going to get back to some graphing. You guys need some practice with the graphing. Some of you do. Especially stuff like 37. And then we talked about this new letter E, so we're going to talk about how to graph E to some power, right? So I'm going to do 2 of these with you and leave the other 2 for you to do. So when you're graphing, you have your base to the power plus some number over here. In this case, it's 0. And that number right there is going to be the horizontal asymptote. If I change that number to 1 or 2 or 3, it moves everything up or down, and it changes the horizontal asymptote as well. So by default, it's going to be at the x-axis. Okay. So it's not adding to the exponent. So like this up here, that moves it left or right. So it wouldn't be part of the exponent. It'd be it'd be a separate term. Okay. So this right here has a horizontal asymptote at y equals 0. And then we just need to find a few other points. So x and y, the easiest thing to do is make our exponent equal to 0. So if I plug in 0, I get e to the 0, which is 1. So that's a nice one to get. If I plug in a 1, I get E, and E is about 2.7. Good. Okay. So between 2 and 3, about right here, at 1, comma E. And without a calculator, that's probably as much as you're going to want to do on that part. And so normally I want 3 points, but with E, I'll accept 2 points if you don't have a calculator. If you have a calculator, then you can get another point. You can find out what E squared is. Or here we could do this. We could say here's 2. So this point right here would be 2E squared, and not label our y-axis. Okay. 37. So if you notice a negative in front of the x, let's make x positive. Okay. So we get f of x is equal to 3 to the. I'm going to factor out that negative. So if I factor out that negative, I'm left with x minus 2. Right? Which is a form we're more used to seeing. And that negative, I'm going to make that negative belong more to the 3 than to the exponent. So I'm going to separate them. Make this 3 to the negative 1, and then put the exponent as x minus 2. So my 3 to the negative 1 is my base, and that's actually what? 1/3. So we had a little extra work to do at first, and now we're ready. What's my horizontal asymptote going to be? Still got a +0 over here, so my HA, horizontal asymptote, is going to be at 0. Yeah. Well, it's x is 2 is positive up here, right? But when I factor out a negative, 2 becomes negative, x becomes positive. So it switches the sign. So we still have our horizontal asymptote at the x-axis. And now we just need to find some values. Now, if your exponent is not just an x, you still want to make that exponent equal to 0. So you want to think, what x value would make my exponent 0? 2. Right? Because if I do that, I'm going to get 1/3 to the 2 minus 2, which is what? 1. You have 1/3 to the power of 0, which is 1. So 2, 1 is going to be a point. It's always the easy one to go after when you have an exponent. If I go for a positive exponent, like 1/3 to the first, 1/3 to the second, it's going to be a fractional. Let's go for an integer, though, if we can. So what would be another good number to plug in? What would happen if I plugged in a 1? I get 1/3 to the 1 minus 2, which is 1/3 to the negative 1, which is 3. So if you have a fraction, you actually want a negative exponent to get rid of your fraction. Okay. So at 1, we're up at 3. And let's pick one more. What would be another good one? 0. What's it going to be when you plug in a 0? Good, 9. So this thing drops down. Label those points. We have our graph. Okay, I'm going to stop there. And your homework's like that, and you can keep working through those.